Welcome to a presentation of position normal distributions for efficient rendering of specular microstructure, implemented in PBRT. Before we begin our presentation, we would like to give a brief introduction of related work concerning microfacet models. In 1967, Torrance and Sparrow introduced an early microfacet model to be used for metallic surfaces. Torrance-Sparrow is a microfacet model. That means that it treats surfaces as a collection of minuscule faces that each can have different surface normals. These microfacets can be thought of as an approximation of the surface at microscopic level. That is, in physical reality, materials are not perfectly smooth. At macroscopic level they might look smooth, but at the smallest level of detail they exist of these minuscule faces that can possibly face different directions. On very smooth surfaces, like a perfect mirror, the surface normals will all have the same or very similar normals. On rough surfaces, like a rock, the surface normals can have different random directions. Torrance-Sparrow uses a collection of perfectly specular and smooth microfacets. The Cook-Torrance model is described by the formula visible on the top left side of the slide. In this formula, R stands for the outgoing radiance at the point where we are calculating the P-BRDF. Ka is a constant ambient term. The rest of the equation iterates and sums over the light sources. In this sum, Lc stands for the light intensity, and .L represents the dot product between surface normal and incoming radiance direction. Both of these terms are multiplied together with a final factor that contains the ratio of diffuse versus specular reflected light, weighted by 1 minus S and S respectively. This parameter S also represents the conservation of energy well, implying that we can never reflect more radiance than came in. The diffuse reflectance is denoted by Rd, which is the constant. The specular reflectance is described by Rs, for which the formula is shown on the top right side of the slide. This is where the Cook-Torrance model really becomes interesting. In the equation in Formula 2, we can see that the surface normal N and the incoming light direction L dot product in the denominator are cancelling out the extracted dot product of Formula 1. Let us now take a look at the numerator, d times f times g. In this numerator, d, f, and g are three pluggable functions that together make up the resulting specular reflectance in the Cook-Torrance model. There is a wide variety in implementations of these functions. Let us talk about the functions d, f, and g in more detail now. We'll start with the function that has the most impact on the final shading result, d. This is also the function that is most relevant to this video, as a paper that we have implemented in PBRT actually proposes a new method to model this function. D stands for the normal distribution function. It models, as its name implies, the distribution of normals in a certain area on the surface. So given a vector, it gives us back the probability that a normal points in the same direction of that vector. As an example, let's take a mirror on which we want to calculate the amount of reflected specular light at a point in an outgoing direction, given the incoming direction. In other words, we would like to calculate the P-BRDF at that point. Recall that the amount of specular light reflected is weighted by the dot product of the normal and the half factor. Therefore, the more similar the half factor is to the surface normal, the higher the reflectance response will be. So if we pass our half factor to the normal distribution function, d, it will tell us the probability that the surface normal on that point is equal to the half factor, which can be seen as a measure of similarity between the half factor and surface normal. For a perfect mirror, the normals are going to be very stable, and therefore the distribution will be mainly centered around one direction, as is shown on the graph on the right side of the slide. Now we'll also briefly introduce the functions f and g. G is the geometric attenuation function. It accounts for the shadowing and masking of microfacets by another microfacet. So g gives us the fraction of total microfacet area over differential area that is visible in the given direction. Lastly, the Fresnel function. It accounts for the Fresnel effect, which says that rays with high incidence angle are reflected with more specularity. Fresnel equations tell us how much light of the incident light is reflected. We'll now talk about the paper that we've implemented in PBRT. We'll mainly talk about how d, the normal distribution function, is normally modeled and how the paper does it differently. So the normal distribution function, or otherwise called NDF, that was introduced before, is traditionally often modeled as a smooth Gaussian-like distribution of normals. Examples of these distributions are the Beckman-Spicicino and Trowbridge-Wright distributions that are already implemented in PBRT. In theory, however, it can be any distribution, as long as it's normalized. The smooth Gaussian distribution works for some materials, like smoother materials and plastics, but it has difficulties reproducing very high frequency effects that we can see on microstructures, such as glitter and specular glints. Examples where we see these effects in the real world are on materials with surfaces that contain flakes, or other materials like brushed metal or damaged surfaces that contain scratches. These are exactly the effects that the paper wanted to model in an efficient way, so they have taken a different approach to model the NDF. In reality, the distribution of normals may be much less smooth than the curve of one Gaussian. Moving over the surface, the distribution of normals can quickly change in areas with high frequency effects like scratches or flakes. Therefore, they attempt to model the distribution using a mixture of Gaussians. They first pre-process a high-resolution normal map that represents the ground truth of the microscopic surface. This normal map is approximated by a collection of 40 Gaussians. These Gaussians are called Gaussian elements. Each of these Gaussians model the local position normal distribution around the point they are placed. The reason why they are 4D is because they are modeling both the 2D position on a normal map as well as the surface normal distribution on that position. Normals can also be represented in 2D by projecting them down on a disk. The density of 4D Gaussians can be modified. The ideal density depends on the normal map frequency content. We chose to go with 1 Gaussian per normal map taxol, as this simplifies some of the implementation details, and the paper mentioned that this was a good density for most materials. After the normal map is converted to a landscape of 40 Gaussians, we can move on to the next step of the algorithm, which is called the P-BRDF evaluation. This corresponds exactly to the classic Torrance-Sparrow BRDF, only the normal distribution D is now being replaced by a new function which we call the P-NDF. This function is the following. The authors of the paper call this a P-NDF evaluation. The P stands for pixel footprint, and the name follows from the fact that we are evaluating the normal distribution around the footprint of the current pixel. One can think of this pixel footprint as a Gaussian region around the intersection point for which we are calculating the BRDF. Now back to the formula. Here GP stands for the pixel footprints Gaussian, which we define by a region size parameter that we included in our code, and GI stands for the 40 Gaussian element at position U. The most right integrand will collapse to a 2D Gaussian, allowing for an analytical solution to the integral over R2 space. This analytical solution is one of the key contributions of the paper, allowing for great speedups compared to previous work. The analytical solution is explained in the appendix of the paper. We have now briefly explained how we can evaluate the P-NDF, that is, how to calculate the output of the D function that is part of the Cook-Torrance microfacet BRDF model. We now shortly discuss how we implemented this mathematical framework into PBRT. First of all, there are 3 main phases to the rendering algorithm. First, there is the value of the BRDF that needs to be decided at the intersection point. This exactly comes down to the P-BRDF evaluation that we have discussed in the previous slides. Since the underlying integrator performs stochastic Monte Carlo path tracing, we will need a stochastic notion of sampling new directions. This is where the next 2 phases come in. In the second phase, we sample a direction that the ray will bounce to. This is done in 3 steps. We first select a random point U in the pixel footprint GP. Then we sample a Gaussian element GI that covers the point U. And finally, we sample a random normal from this Gaussian element. Since PBRT expects normals as 3D vectors, we first transformed the Gaussian element's 2D mean normal back to 3D, and then sampled each dimension according to the standard deviation. This is done in the method called sample WH, part of our normal to NDF converter clause. In the final phase, we have to account for the probability that this ray direction was chosen, as the division by the sample's probability is an essential part of the Monte Carlo estimator. Our sampling algorithm is sampling according to the NDF, so this means that the probability of taking a certain sample corresponds to the P-NDF itself. To retrieve the probability value, we can therefore just do another P-NDF evaluation. This PDF method was overridden in the glitter distribution class, which inherits from the microfacet distribution class that is part of PBRT. In summary, the relevant code that we have contributed can be found in the normal to NDF converter class, the glitter material class, and the glitter distribution class. Before we show some of our results, we would like to briefly talk about some of the flaws of our implementation. As can be seen in the rendering, the specular high-frequency glint effects that we expect seem to appear with a lower frequency. If we had more time left, these are the following things that we would try out first to resolve this. The first thing is, as we explained in this video and the paper, the code that samples a new ray direction according to the half factor at the intersection point first samples from the Gaussian pixel footprint to obtain a Gaussian element, from which we then sample a normal. In our implementation, this Gaussian element is sampled from a square region around the intersection point instead. We would therefore like to transform the square region into a Gaussian footprint region. The second thing is that smaller light sources could also better visualize the specular effects that we expect. Larger light sources tend to produce big highlights rather than the high frequency effects that we are trying to model. Another thing that we could try is to increase the density of 40 Gaussian elements. This, however, complicates some of the implementation details where we could now work around, because we have exactly one Gaussian element per normal map texel. A good reference to compare our implementation with would be a rendering that uses the complete high-resolution normal map from which we sample normals together with a perfectly specular BRDF. Another thing influencing the appearance of effects can be the resolution of a normal map used in pre-processing. We have worked with mainly 8000 by 8000 normal maps. However, in the paper they mention high-resolution normal maps of even 200,000 by 200,000. Note that this also requires a great amount of memory during pre-processing.